All right, we're just going to do a quick quadratics review before we do a bunch of problems in class. The first thing I'm going to talk about is factoring. So let's say we have a quadratic, which is just something whose highest leading term is something it's something with a squared. X squared is the biggest degree that we're raising an x to in our equation. So let's say if we have y equals x squared minus x minus 6. If we want to look for its x-intercepts or we want to find the zeros, roots of the function, factoring might be the easiest way to do that. So what we want to do is break this up into two linear factors that are multiplying by each other, that are going to multiply to get back to this original quadratic. So we're trying to basically undo the multiplication that got us to our quadratic. So what we're really looking for is two linear factors, right? Two things that have a degree of 1 that are multiplying together. And their first two terms need to multiply to be x squared. So we're going to have x and x, right? X times x has to be x squared. And they both have to be 1 because we have 1x squared. And the only way we can get 1 is 1 times 1. And now our chunks that are going to go on this side, right, have to multiply to be -6 and add to be -1. So we need two things that multiply to be -6 and add to be -1. So what are some factors that do that? What multiply to be -6? So a times b equals -6. A plus b equals -1. Well, so a couple factors of -6, we could do -3 and and 2, or we could do -2 and 3. We could do -6 and 1. We could do -1 and 6. But the one jumping out at me pretty quickly is this first one. Oops. Is this first one, right? -3 and 2. So if I have x minus 3 and x plus 2, -3 times positive 2 is going to be -6, and -3 plus 2 is going to be -1. So this is great. These are our factors, right? So this is our same quadratic, but in factored form. And if we aren't sure if we're right, we can test, right? Just by redistributing. Some people call this foiling because it's like first, outside, inside, last. But we're really just distributing or multiplying through both of these parentheses. And we'll come back to x times x is x squared. -3 times x is -3x. X times positive 2 is plus 2x, and then -3 times 2 is -6, and then when we combine like terms, we get x squared minus x minus 6. Awesome. Then we can have other factoring that sometimes can get a little bit trickier. In this one, it's really the same, but we just have 1 times -6 here, right? We have 1 out here times -6. So we want the same thing, same kind of setup. Right? If our leading term is not, our leading coefficient is not 1, right? If we have something a little bit different, let's say we have 3x squared minus 5x minus 2. This is a little bit trickier to factor because this 3 out front makes it a little bit harder. We have to have a 3 and a 1 somewhere at the beginning. Again, though, we're looking for two linear factors that are going to multiply together to come back to this original quadratic. And same thing, we want our two parts of our factor, right, to be a times b, right, is going to equal, we're going to do what's called factoring by grouping because of this 3 in front. A times b are going to be our two, I guess, like, I should backtrack. Basically, what we're going to be doing is breaking up this middle term into two parts. And that's going to be an a part and a b part. So we want a times b to be equal to our first leading term coefficient times our constant, right? Or 3 times -2, which is going to be -6. And we want a plus b to equal the thing that's in the middle, right? What it was before, -5, I guess. So a times b has to equal -6. It's the a term, right, our leading coefficient times our constant, and then a plus b want to be our b term. And so what we're going to do, what two numbers make this happen? Again, what multiplies to be -6, -3 and 2, -2 and 3, -6 and 1, -1 and 6. I found a winner, -6 and 1, right? Those are going to add up to be -5. But those aren't going to go right into our factors, right? We need to keep in mind this 3 in the front. So I'm actually going to erase this. There's going to be one more step in between. Actually, a couple more steps, I guess. I'm going to rewrite this as 3x squared minus 6x plus 1x minus 2. So I've just rewritten -5x as minus 6x plus 1x. And this is going to allow us to do the grouping part of the factoring by grouping. Now we're going to factor it in chunks. So I'm going to pull out a 3x of just, or actually I'm going to pull out the greatest common factor of just the first bit, which happens to be 3x. So now we have x minus 2, right? 3x times x is 3x squared. 3x times -2 is -6x. And now I can do the greatest common factor of x and -2 is just 1, right? X minus 2. And if you factor by grouping correctly, you should get two things that are the same. Because now I can factor that out, x minus 2. And what's x minus 2 factored out of this whole thing? What do I need to multiply it by to get back to my original? 3x plus 1. And those are my two original factors. And if you want to check to make sure you're right, you can distribute and do x times 3x is 3x squared. X times 1 is plus 1x. -2 times 3x is -6x. And then -2 times 1 is, -2 again. And then we can just combine like terms. 3x squared minus 5x minus 2. These are the same. We did it right. So our factorization is this bit in the middle. So why is factoring important? So if we got the two factors in the last one was y equals x minus 2 and 3x plus 1, right? That was our factorization. Why do we care? Why does it matter what the factors are? Well, if we wanted to know what are the x-intercepts of this quadratic, we can just set this equal to 0, right? The x-intercepts are where y equals 0. And now, based on the zero product property, which hopefully we've heard of before, ZPP, zero product property, if either of these factors, right, equals 0, the whole thing equals 0, right? 0 times anything is equal to 0. So if x minus 2 equals 0, the whole thing equals 0. If 3x plus 1 equals 0, the whole thing equals 0. So my two x-intercepts for this quadratic are going to be at x equals 2 or 2 comma 0. X-intercepts are always a coordinate point, right? Or at -1/3, right? -1/3 comma 0. I skipped a bit of a step in there. Basically what I just did was 3x equals -1 by subtracting 1 on both sides, and then x equals -1/3 by dividing by 3 on both sides. So these are our two x-intercepts of this quadratic. These are called x-intercepts. They're called roots as well, or zeros. Sometimes people call them solutions. There are three different forms, shifting gears a little bit, there are three different forms of a quadratic equation. We have standard form, which is written as ax squared plus bx plus c equals 0. Where a, b, and c are all constants. They're all either a coefficient or a constant, but they're all just numbers. We have vertex form, which is y equals a times x minus h all squared plus k, where the vertex is at h comma k. And we have factored form, which we just talked about, which is y equals a times x minus r, x minus s. R and s represent our x-intercepts. So this has x-intercepts at r, 0, and s, 0. Again, r and s are just numbers. And last thing I want to talk about in this video, and we'll talk more about it because I'm sure there'll be some questions, is completing the square. Completing the square and the quadratic formula are basically the exact same thing. And we'll talk about how they're the same thing another time. But so the reason why I bring it up is because if you are in standard form, so if we look at our equation that we had at the beginning, x squared minus x minus 6, this is in standard form, right? If I want to get this into vertex form, there's a couple ways I can do it. The vertex of a parabola is at x equals negative b over 2a, right? Or negative 1 over 2 times 1 in this case. And then you can plug that x value that you get into your equation and find the y value, and then you can find the vertex form, and the a values are always going to be the same. So you can do it that way. You can also do it using completing the square, and I think it's kind of a fun application. So let's refresh that. So if I'm going to complete the square, I'm going to try to, my goal, remember, is to get this into vertex form, so I want it to look like vertex form. So I'm going to keep this on the same side. Sometimes if you're solving for 0, like solving for where x equals 0, you might move the constant over, but I'm actually just going to throw it off to the side there. The first step in completing the square is you need your leading coefficient to be 1, and it already is, so I don't have to do anything. Now I'm going to add my b value, negative 1, divided by 2 all squared. And this is going to create my perfect square or complete the square in completing the square. But when I add it, I have to add it again. Or sorry, not add it again. I usually add it to the other side, or I have to subtract it. So I have to cancel it out and balance out the equation. So I have minus negative 1 over 2 all squared. So now I can rewrite this. And I have x squared minus x plus a quarter minus 6 minus a quarter. So we have the same equation that we started with, just plus and minus 1/4, which cancel out to be 0, so we haven't changed anything. So now I can rewrite this again. And the whole point of completing the square, of adding this opposite of b over 2 squared term, is now we have a perfect square, or something that is times itself, right? This is really, this chunk factors to be x minus a half times x minus 1/2, right? And we can carry our constants, right? Or we can rewrite this as x minus 1/2 all squared. And negative 6 is really just negative 24 fourths. Minus 1/4 is negative 25 fourths. And so now we've rewritten this. We've completed the square. We've made a perfect square in here, right, in this first bit. And that basically creates our vertex form. And we have our h and our k. So our vertex is going to be at 1/2, comma, negative 25 fourths. And if we also, the thing that's nice about completing the square or having a perfect square of any kind is that if we want to solve for where this equals to 0, we can move the 25 fourths over by adding it to both sides. We can take the square root. Love that. Square root of 25 fourths, that's a nice one. Right, now we can have plus or minus 5/2 equals x minus 1/2. And so now x, right, equals 1/2 plus or minus 5/2. And these come out to be pretty nice. 1/2 plus 5/2 is 6/2 or 3. And 1/2 minus 5/2 is negative 4/2 or negative 2. And those are our answers from our first factors that we did at the beginning.